last class we finished up with the noise of the active mixer, and as promised we are moving on to the passive mixer implementations. So the reason these mixers are passive is because the devices involved here are not biased in any particular operating point in the saturation region, and they do not have bias current flowing through them. And so in other words, you are using the device purely as a switch between the off and the triode region. So you are using the MOSFET as a passive switch, and there are no amplifying devices. So let us take the simplest example of this. Which is a voltage mode return to zero passive mixer. By the way, if you want to refer to this, refer to Razavi section 6.2. So that is what I am following closely for the class. So first we'll look at the voltage mode return to zero passive mixer. So we'll take the example of a switch which has the LO signal which is either 0 or 1. It's a perfect 50% duty cycle square waveform which is going from 0 to 1 and back. And the input is given on the left side of the switch and the output is taken across the resistor. So for example, if you had a sinusoid like this and you were sampling it at some frequency, so I'll change it a little bit. So you get something like this. And so on, right? So you're basically, when the switch is on, you're sampling whatever is there in the input to the output, and when the switch is off, the resistor sets it to 0. So in other words, if the input was a double-sided waveform at plus or minus omega RF, in the frequency domain, this is convolved with the, what is it convolved with? It is convolved with the Fourier transform of the LO waveform. But what we'll do is we are interested only in the IF, right? So we'll take the first harmonic. We'll analyze it in more detail for the sampling mixer, but here we'll say it is just convolved with the fundamental of the first harmonic of the omega LO. What is the amplitude of the fundamental? For a square wave going from 0 to 1, the amplitude of the fundamental is 1 over pi on each side. Okay, so your RF waveform is convolved with this to give you your IF output, and the amplitude of these also goes down by pi. No, all you have to do is filter out the output to get the IF waveform. So the IF will have, so the LO has multiple harmonics, you can do the full calculation, and you are interested only in the fundamentals, and if you actually just low pass filter the output and look at only the IF, you will get whatever was at the RF translated to the IF.
No, I'm not talking about the other harmonics.
Okay.
What I'm saying is,
No, this output can be taken as a voltage, it can be sent into an amplifier, for example. into the input of a, let's say, a common source amplifier, right? So the assumption is that you are okay.
My argument is the problem always is depending on how the, since it's not a zero order.
Yes.
If this is zero order, it's not.
Yes.
And you're not taking a point sample.
Correct. You're taking a continuous sample. Correct. That is right. Okay. So yes, of course, the assumption is that IF is much smaller than LO. In a receive mixer, that is absolutely true. Okay. What you're saying is right, because we can choose to not look at the fundamentals. We can choose to look at the some nth, let's say some nth harmonic of the LO, and mix that with RF and use that translation as our desired frequency. We can always choose to do that. The only thing is we'll get a much smaller amplitude at the output. The conversion gain will be very small. Okay. Apart from that, you're absolutely right. You will see a sync kind of shaping of these impulses. Since we are looking only at the fundamental, we are seeing this. In the case of the sampling mixer, we are going to do the math in a lot more detail in a few minutes. So we'll understand exactly how it behaves. Because this is a much simpler example, I just decided to just look at the fundamental and move on. So if you look at the S of t or SLO of t, this has a fundamental which is 2 by pi cos omega LOT, because it goes from 0 to 1 and back. And the conversion gain for this type of mixer is 1 by pi, which is approximately minus 10 dB. So it has a conversion loss. SLO of t has an average value of 0.5. What does that mean? What significance does this have? Yes. So what? It has a DC value of 0.5. So what happens? Your RF directly goes through to feeds through to the IF port. Okay. RF appears at the IF port with a gain of 0.5. Okay, which is actually larger than your IF. That's just something to keep note of. Because the gain for IF is 1 over 3.14, 1 over pi. If you have some kind of even order distortion prior to mixing, in the mixing path, that will get directly translated to your port, to your output port. So for example, if your even order distortion has a component, let us say this is a direct conversion receiver, your even order distortion has a component falling around baseband, around DC. What will happen is, because this has a gain of 0.5 from the RF port to the output port, you will see that the even order distortion will go right through the mixer with a gain of 0.5, and this will cause DC offset problems or a time varying offset or whatever it could be. Causes IIP2 problems. How do you get rid of this? High pass filter. No, that may not be the best thing. You may need a huge capacitor. Make it differential. So you move from a single switch to a single balanced mixer. Okay, so the single balanced mixer will get rid of the DC component and has twice the gain. Okay, so this and no DC component at the IF port. So this is really the mixer we are interested in, because it's not common to have resistive loads in the in IC designs. Plus, the other reason is you will find that the sampling mixer actually performs better than your resistively loaded mixer. So this is of more importance to us. So we are going to analyze it in a little bit more detail. So instead of a resistive load, we are going to assume that there is a capacitor there. So the difference between this case and the previous case is that, let us say the input had some waveform like this. Just expanded it a little bit. So the output not only samples it but also holds it, right? So if you were to sample it, so what you'll find is that, let me start off from here. It does this, follows this, something like this, right? At every time when the switch turns on, it gains a new value of RF and follows it till the switch turns off. So let us say this is, input was x of t and output was y of t. What we are going to do is, to make our analysis easier, we are going to split the output. So this is y of t. We are going to split the output into two parts. Okay. So we are going to split it as okay, so I'll take this. I'm going to split it into two parts. One part is going to do this. Okay, I am going to take only the tracking part, right? At the other end, I am going to set it to 0. So I'll call this y1 of t. What is this? This is exactly the same as your resistively loaded mixer, the return to 0 mixer. So you're tracking it for some time and then returning it to 0. What is the other portion? The other portion is just a sample and hold. So it's going to sample it. So you won't see the tracking portion. So you'll see this portion. And so on. Okay? This is the other half of the cycle. During this portion, I'll just use this. I'm just showing the sample and hold behavior. So this is your, this is your return to 0 output. And y2 of t is the output stored on cap. Is the output stored on the cap when the switch is off. Okay? So now we need to calculate exactly what y of t is. So y of t is y1 of t plus y2 of t. So we'll calculate y1 of t and y2 of t separately. So we already know y1 of t is the same as before. We expect a conversion gain at the IF port of 1 over pi. So we are going to write y1 of t in this way. What is y1 of t is going to be x of t, okay, multiplied. So what is this what is happening here in y1 of t? It's multiplying by 1010 for certain portions, and I can look at it as taking multiplying this by, it is actually being multiplied by a square wave, but I am going to split the square wave as a pulse around from 0 to TLO by 2, convolved with an impulse train. That will give you exactly the same behavior. So I'll represent this. I'll use the same notation as in the textbook. I'll use this kind of a pulse notation for the pulse from 0 to TLO by 2. And convolved with where this function is nothing but this function, this pi kind of function is nothing but this, represents this pulse from 0 to TLO by 2. So now we just have to evaluate y of f from this y1 of f from this y1 of t. So to do that, we'll remember a few identities. So an impulse train in the time domain is also an impulse train in the frequency domain. So that is the first one. X of t minus capital T is nothing but e power minus j omega t x of f in the frequency domain. And this pulse from 0 to t by 2, when you go to the frequency domain, is the sinc function. Okay, so I'll write it in terms of the exponential. Okay, I'll write it as the exponential. So 1 minus e power minus j omega t by 2 by j omega. So now I can write y1 of f in terms of x of f. Now the multiplication becomes a convolution. 1 over j omega into 1 minus e power minus j omega t LO by 2. Multiplied by the impulse train in the frequency domain. Okay, so this is what y1 of f is. Now I can, to make things easier again, I'll say inside this, if I set k equal to plus or minus 1, that will give me my IF spectrum, because I am really interested in the product of RF and the LO frequencies. In other words, the RF frequency translated by the LO frequency and not by its harmonics. So I am going to set k equals to plus or minus 1 in this expression to get the IF spectrum. So y1 of f at if is nothing but x of f convolved with, what do I have to do? I of course get two delta functions there, so I'll really have to evaluate this at those 2 points at k equal to plus or minus 1. That gives me plus or minus t LO by j pi times 1 by t LO okay. That is what this gives me. So this is nothing but x of f minus f naught by j pi, no, sorry, f minus f LO by j pi minus x of f plus f LO by j pi. So as expected, for the first portion the conversion gain is 1 over pi. This is what we expected before. Okay, the conversion gain is 1 over pi. The only difference is there is a phase shift. There is also a phase shift of 90 degrees because of the j term. So if you look at it in the frequency domain, so what we are saying is, so we are taking this, the square wave, and writing it as your single pulse from 0 to TLO by 2 convolved with a pulse train. Okay, and then we are saying you take your RF spectrum, okay, and then convolve it with this, with a sinc kind of function, where okay. Remember that because the pulse is from 0 to TLO by 2, the sinc 0 crossings will be at 2FLO. Okay, and this is what gives you your IF spectrum. With a 1 over pi kind of conversion gain. Okay. So now we have found out the first portion of the gain of the first portion. We need to find out the gain of the second portion and then add the two together to get the overall gain. But it should already be clear that this particular, the sampling mixer potentially has more gain than the return to zero mixer, because even one part of it has the same gain as the return to zero mixer. Okay. So again, y2 of t, I am going to write it as an impulse train, okay, sampling the input, followed by convolution, okay. With a square pulse, okay, and we can again find out mathematically what that gives. So this is nothing but x of t multiplied with the impulse train convolved with the pulse from 0 to TLO by 2. Is that clear so far? So I can find out y2 of f is nothing but x of f convolved with the impulse train with the frequency with the Fourier transform of the impulse train, which is 1 by TLO delta of e power minus j omega TLO by 2, because it's shifted by TLO by 2, times delta of multiplied with 1 over j omega into 1 minus e power minus j omega TLO by 2. Is that okay? Is everything okay, or is it going too fast? Pretty straightforward, nothing fancy. Now again, I can set k equal to plus or minus 1 to find out my IF output. So y2 of f at the IF port gives you 1 over TLO. So I have to evaluate x of f at k equal to plus or minus 1. It gives me multiplied with now, of course, this portion, I'll write it in blue because I have still not evaluated it at omega equal to omega IF. The reason is, it really depends on the relative values of omega F and FLO, omega LO, right? Because if omega IF was much smaller than omega LO, I can make an appropriate approximation. So let us take that case, which is the case in a receive mixer. If omega IF was much smaller than 2 omega LO, so e power minus j omega IF TLO by 2 becomes approximately 1 minus j omega IF TLO by 2. So I can make this approximation when omega IF is much smaller than omega LO. And y2 of f evaluated at the IF frequency becomes approximately minus x of f minus FLO by 2. Okay? So now we have found out y1 of f and y2 of f. We just need to find out y of f, and more importantly we are interested in the magnitude of the at the IF port, and because there is a phase shift of 90 degrees for one of them, we'll take the square root of the sum of the squares. Okay. So the actual conversion gain is this root of 1 over pi squared plus 1 by 4, which happens to be 0.593 for this mixer, which is better than your original 1 by pi which you had before. So now if you assume that I create a single balance version of this mixer, I'll get double this gain. So if I were to always LO plus and LO minus. Okay, if I create the single balance version of this, has GC which is twice 0.593, which is approximately 1.48 dB. Right? So as it turns out, even the passive single balance mixer has a gain which is larger than 0 dB. It actually has a positive gain. Why do you think this is? Does it seem surprising? Does it seem surprising that you have a passive mixer but it has a gain which is larger than 0 dB? Primarily it is because of that. Okay, because if you take a square wave, which is what you are driving the LO port with, the fundamental of that is actually larger than the amplitude of the square wave. Okay, so you can get a positive conversion gain. Okay, so we have looked at the single balance mixer for these two cases. What about the double balance mixer? Let us go back to our active mixer. Can you tell me what the difference between the single balance and the double balance mixer was? We inverted the RF and inverted the LO also and then added the outputs. Right? What was the conversion gain of the double balance mixer, active mixer? Compared to the single balance mixer? So what is the conversion gain of the double balance mixer? So Ananya, what is the conversion gain? Can you go back to your notes and check? We did it, right? We did the analysis. Which one? Which portion? For the single balance, because you get twice. It's 2 by pi. The gain is still 2 by pi. We got a 4 by pi term when we did the analysis in class, but we had a 2 IRF at the input. Okay, we assume plus or minus IRF. So the gain for the double balance mixer is still 2 by pi in the active case. So if I were to build a double balance mixer of either of double balance version of either of these two mixers, what gain will I get? Will I get the same gain, twice the gain? What will happen? So let us take the case of the resistively balanced mixer. resistively loaded mixer. Okay, let us take this case, LO plus, LO minus, LO minus and LO plus. Okay, I am looking at VIF plus and VIF minus. What is the gain of this if I look at the output, differential output? I am getting twice the RF swing, I will get twice the IF swing, I will get the same gain. For this is 2 by pi, which is the same as the single balanced version. Okay. What if I do the same thing, except I am going to replace these with capacitors. What happens? So there is a slight difference between this case and the previous single balance mixer case. The difference is that whether it's a resistor or the capacitor, but let's look at the resistor case. The difference between this double balance mixer and the single balance mixer is that in the case of the single balance mixer, in the case of the single balance resistive mixer or the capacitive mixer, let's look at this guy also. Either output, okay, only one of the output is asserted at any time. While one side is tracking, the other side is holding, and vice versa. Whereas in the case of a double balance mixer, you actually have tracking and holding going on both sides. Okay. So in reality, the exact load at this point doesn't matter because you're looking at the output differentially. The load is actually, both outputs are getting asserted all the time. So if you actually look at a double balanced capacitively loaded mixer, its gain is also 2 by pi and it is lower than that of the single balanced mixer. Okay. Even for the so in other words, if you think of it, it's easier to see it with the resistively loaded mixer. The original mixer we had a track and then a return to zero. Whereas if you take the output differentially, this has always only a track. Either you are tracking the positive side or the negative side of the input waveform. So you can think about it that way. You do not have a return to zero in the case of the resistively loaded mixer. And so this resistor, the load really does not do anything because you are looking at the output as a difference between those two nodes. You are not floating any node at any time. And the same thing goes for the capacitively loaded mixer also. And so the gain is actually lower by around 5.5 dB compared to the single balance mixer. So question is, would you ever use a double balance mixer in this case? The RF feed through is always removed even in the single balance mixer. It is the LO feed through which is not removed. Okay? Yes, that is true. If you want to remove the LO feed through, you might want to do the single balance mixer, but you are actually getting a 5.5 dB. That's almost a loss, right? Compared to the single balance mixer. So note that this is happening because you are taking the difference of the voltages in the voltage domain. What you can choose to do is actually convert these voltages to currents and then add or subtract the currents. If you do that, then you are still allowing these nodes to, in the case of the resistively sampled mixer, you are allowing it to go down to 0 and back to track, and therefore you will still get the same gain as you got with a single balance mixer with all the advantages. So if you want to use this, you could choose to add outputs as currents. To preserve the conversion gain which you had for a single balance mixer. Okay. So for example, instead of looking at the voltage here, you could actually put in a common source amplifier and then add the two currents. So then it is no longer a differential case, it's a pseudo differential case. Okay, and you could choose to add them as currents. Okay, so far the passive mixer looks quite good, right? And you will find that this is increasingly being used when used in receivers. You could,
you were isolating the transformer in the whole.
correct, that's right. Now you could also choose to drive it with a current instead of a voltage. The same mixer, the same passive mixer, you could choose to drive it with a current instead of a voltage. And you will find that the behavior of this mixer is quite different. In fact, when I say behavior, I mean starting right from the input impedance. What is the input impedance of the circuit? Correct. So in reality this is a time variant circuit. So the input impedance will have to be calculated because you not only have one particular frequency, you have many frequencies to take care of, and the input impedance is not so easy to analyze. We will probably, in next class I'll give you an idea of how we go about it, but really the important thing to note is that because the circuit is time variant, the input impedance, looking in impedance as seen with a voltage source and as seen with a current source are different. When you have linear time invariant circuits, obviously the input impedance is independent of whether you try to drive it with a voltage source or a current source, but unfortunately in this case it is not the same. Okay. But what we'll do is we'll say that if you were to drive it using a current source, what kind of load would you prefer? Let us say this is my IRS, my LO switches are there. What kind of load would you prefer? Something with a very low impedance, right? What offers you a very low impedance? A capacitor. No, this is the IF port. Okay, this is the IF port which may even be baseband. Let's take the case of a direct conversion receiver. That's the simplest case, right? Inductor. No. Why would you want to use inductors here? So the easiest way to actually sense this and get a zero impedance is to take the output through a transimpedance amplifier, which gives you a virtual node at its input. Okay. So this gives you a differential virtual node, and therefore for the differential current flowing in, it looks like a very low impedance, and this current actually flows through these impedances to give you a voltage. You can embed some filtering inside it if you want, and so on. This is the preferred way of working with these current mode passive mixers. Now, if you have an input which has both in phase and quadrature components, so it's a complex signal, you will not only need to multiply it with LO, you will also need to multiply it with the quadrature phase of the LO to actually extract out the baseband quadrature. So if I call this LOI, and this gives me BBI, I can choose to if I do this, I can extract out the quadrature component of the baseband, separate it out from the in-phase component of the baseband. I can have two separate DACs and so on. From beyond this point, I'll have two separate in-phase and quadrature channels. Okay, and this is quite often the preferred way of dealing with these because it offers several advantages. So first of all, because you are dealing with current, all these nodes are very low impedance nodes and therefore very broadband nodes. Okay, so if you are really interested in a very broadband signal, okay, or if you are interested in a multi-band system, you will want to have, starting from the mixer onwards, you can use the same mixer and baseband to actually process multiple RF bands. So I could have 10 LNAs, but all their output currents actually combined at these two nodes. All their outputs combined at these two nodes. Okay, and they will all flow through the transimpedance amplifier. At any time, one LNA is on, but I may want to have a multiband receiver whose mixer and baseband and so on are all common. And again, if you want to do noise analysis for this mixer, just like you had in the active mixer, you had multiple noise bands folding down, you will have the exact same effect here. So what we'll do is next class we'll try to go over some portions, at least we'll try to get a start on the noise analysis. Probably the full noise analysis may be too much at this point of time. So we'll try to at least get a head start and we'll look at the results and see what it looks like. Okay. The important thing to note is that obviously the noise will get translated in frequency. The second thing is you will have to keep track of correlations. If you try to separate the outputs, for example, into Y1 of F and Y2 of F, and if your noise will get, the noise going through the two paths could be correlated. So you'll have to keep track of that. Okay. So we will stop now and continue that next class.